For most of the rest of the course, we'll be studying planets and moons from the inside out. We'll start with the interiors, because the insides shape the outsides. Then we'll move on to the surface geology. Finally, we'll look at atmospheres. As we do this, we'll start by looking at the processes that affect all worlds, and then use individual planets and moons to give examples of how these processes play out in different circumstances. As a result, these chapters are not divided up planet by planet, or even terrestrial versus Jovian. Instead, they go process by process. So to begin with, we'll look at planetary interiors, the stuff that's hidden beneath the surface.
We'll start by learning about how we study the interiors of planets. Next, we'll look at two processes that shape the interiors of worlds. Differentiation defines the layering inside a world, while compression affects the density and even the phase of the matter deep inside a planet. Finally, we'll look at the heat energy inside planets and moons. We'll see the different ways heat can be generated inside a planet, as well as the ways that heat can flow from the inside out to the surface. This last topic has huge consequences for defining what both the surface and the atmosphere will be like.
We can't see inside a world, nor can we dig very deep into one. Even for the Earth, the deepest hole humans have ever drilled into our planet is only 12 kilometers deep. Not very far compared to the 6,400-kilometer radius of the planet. If you have a typical Earth globe, the deepest hole might make it through the paint on the surface. Since we can't dig far into a planet, we have to use more indirect means to understand what their interiors are like.
The most important source of information about the Earth's interior is seismology, the study of vibrations traveling through the planet's interior. Whenever there's a large earthquake or explosion, the shock from this travels through the Earth. By timing the arrival of different types of waves in different locations, we can put together a detailed picture of the Earth's interior structure. Unfortunately, the only other world that has been studied seismically is our own moon, and that in not nearly as much detail as the Earth. We can also use gravity to study the interior of a planet. The irregularities in a planet's interior show up in the strength of its gravity at different locations. Since an orbiting spacecraft is pulled by this gravity, we can use the motions of the spacecraft in orbit to map out the planet's gravity field, and hence get a picture of its interior structure. We can use a planet's spin to tell us how matter is distributed inside. This happens because a spinning planet bulges at the equator. This picture of Saturn shows how much bulge a planet can have. The dashed line is a true circle. The size of this bulge depends on several things, including the spin rate and size of the planet. But it also depends on whether the mass is mostly concentrated at the center or spread out evenly throughout the world. So by measuring the bulge, we can get a sense of how mass is distributed in a planet.
Finally, we can make theoretical models of a planet's interior that are consistent not only with the observations, but also with the physical forces acting on the interior. For example, we can think of dividing up the interior into layers, and then for each layer, calculate the forces acting on it. Since these forces must be in balance, this limits the density and composition in that layer and helps determine what the next layer down is like. One result of this kind of study is that pressure goes up as you go down under the layers of rock in a planet, just like pressure goes up as you go down under the layers of water in an ocean.
One more way we can get clues about a planet's interior is by studying its magnetic field. For a planet to have a strong magnetic field, it has to have a dynamo operating inside it. A natural dynamo forms when a spinning planet has an electrically conducting liquid flowing inside it. In the Earth, that liquid is liquid iron, but in other worlds it can be water or even liquid metallic hydrogen. So when a planet or moon has a strong magnetic field, This gives us clues about the temperature and composition of the interior.
Magnetic fields can also give us information about a planet's past history. Iron-rich surface rocks carry a remnant, sort of like a fossil, of the magnetic field that was present when they first solidified. By studying this remnant magnetism, we can learn about the planet's magnetic field in the distant past.
On this map of Mars, the red and blue regions show areas where the different directions of magnetic field can be seen. Mars doesn't have a global magnetic field now, but these remnant fields show us that it used to have a warmer, more liquid interior than it has today. This map shows the remnant magnetism in the Earth's oceans off the west coast of North America. The alternating stripes correspond to the alternating directions that the Earth's magnetic field pointed over several million years. This sort of remnant field map helps us plot out the history of how the ocean crust formed. So now that we've seen how we study interiors, let's look at what we've learned about the structure of planetary interiors. There are two main processes that define the large-scale structure inside a planet or moon: chemical differentiation and compression. We'll start with differentiation.
Chemical differentiation is a separation of the interior into layers by density. The denser materials sink to the core of a planet, while the less dense materials float on top. This will happen whenever the materials don't mix well and have a different density. This is the same process that happens whenever oil floats on top of water. Oil and water don't mix, and oil is less dense than water, so it automatically rises to the surface. Have you ever noticed something like this, say, with salad dressing? Inside a terrestrial planet like Earth, this leads to the formation of an iron core with a mantle of rock surrounding it. On worlds that have a lot of ice, like many of the outer solar system moons, there can even be two mantles, an inner one made of rock and an outer one made of ice.
This is a good time to point out the terminology describing interior layers. The core is the innermost part of a world. While this is the densest part of the world, it may not be a very large part of the mass. The mantle is the material on top of the core, reaching almost to the surface of the planet. This is usually the bulk of the planet's interior. Finally, the crust is the thin outer skin of a world. It's effectively the scum that floats to the surface of a planet. While some solid planets have a crust that is hundreds of kilometers thick, in the case of the Earth, the crust is less than 100 kilometers thick, and over most of the surface, it's only about 10 kilometers thick. That means that the Earth's crust is proportionally about as thick as the skin of an apple. In the last two chapters, we've looked at two different ways that different materials can separate out by density. In the last chapter, we saw how the dense, rocky planets form closer to the Sun than the less dense, giant planets. In this chapter, we've now seen why inside a planet, dense material forms the core, while less dense material surrounds it.
However, these two results occur for very different reasons. In this your turn question, I'd like you to compare the processes that give rise to both of them. What's different about the cause of layers inside a world versus the cause of different regions in a solar system?
The next important process shaping interiors is compression. This is simply the squeezing that happens due to the weight of the overlying material.
Compression has a pretty minor effect on the interiors of terrestrial planets. The core of the Earth gets up to a density of only about 8 grams per cubic centimeter because of the weight of the mantle pressing down on the core. This isn't even doubling the density that metal would have otherwise.
However, in Jovian planets, compression has a huge effect on the interior. In fact, it defines the physical state of most of the matter inside these giant worlds. That's both because of their larger masses and because the hydrogen and helium that make up much of their mass is very compressible. It's much easier to squeeze hydrogen than rock. So let's see what compression does to the giant planets, starting with Jupiter and Saturn.
The vast majority of the matter in these two worlds is hydrogen and helium, which explains why we call them gas giants. But this is a bit misleading because, in fact, very little of their mass is gas. On this pie wedge of Jupiter's interior, only the outer section is gas. It's just a few hundred kilometers thick out of the over 60,000 kilometer radius of the planet.
Below this, the pressure of overlying material squeezes hydrogen into a liquid. The darker region here is liquid hydrogen. The transition from gas to liquid isn't a sudden one like the transition from air to water on Earth. Instead, as you sink through the air on Jupiter, it gets gradually thicker and thicker until it turns into a liquid. The deeper we get, the higher the temperature and the higher the pressure. When the pressure gets up to 2 million bars, that is 2 million times the air pressure at sea level on Earth, hydrogen goes through one more change, turning into a liquid metal.
The atoms in liquid metallic hydrogen are squeezed so tightly together that the electrons can travel freely from one atom to another. This is what lets hydrogen behave like a metal. It conducts electricity easily, and it would look shiny and metallic if you could see it, just like liquid mercury, which you might have seen in an old-fashioned thermometer.
Deep in the center of both Jupiter and Saturn, there is a core of denser material. It's only 5 to 10 Earth masses worth, 10% or less of the planet's mass. It's difficult to tell directly what it's made of, but we can make a reasonable guess from the common materials available in the outer solar system: hydrogen compounds, rock, and metal. Notice the conditions here. At the center of Jupiter, the pressure is 100 million bars, and the temperature is 20,000 Kelvin, much hotter than the surface of the Sun. Whatever phase this core is in, it's nothing like rock and ice as we know it. Jupiter and Saturn have almost the same composition, but their densities are very different. Jupiter is more than 50% denser than Saturn. Once again, this is a result of compression. Jupiter is almost 3 times the mass of Saturn. This means that Jupiter's gravitational pull is much stronger than Saturn's, so it's able to compress hydrogen much more effectively than Saturn does. We can see this when we compare the interior structures of the two. Notice that a lot more of Jupiter's interior is liquid metallic hydrogen, while Saturn has a larger fraction of its mass as gas or ordinary liquid hydrogen. As a result, Saturn is almost as big as Jupiter, even though it has much less mass.
This is a general rule for hydrogen-helium worlds. As you add mass to them, they don't get much bigger. Instead, they get denser as the greater gravity compresses the interior. It's sort of like making a big pile of pillows. As you put more pillows on the pile, the bottom pillow just gets squeezed down smaller, and the whole thing doesn't get much taller.
In fact, Jupiter's near the maximum size for a world like this. If you kept adding mass to Jupiter, it would eventually start getting smaller, not larger, as the added compression dominates the size. This trend only reverses when the planet gets large enough that the core starts going through hydrogen fusion and it turns into a star. So what about Uranus and Neptune? Their masses are small, so if they were made out of hydrogen and helium, they should have very low densities, much lower than Saturn's. But in fact, Uranus and Neptune are denser than Jupiter. So what would cause that?
Composition, of course. Uranus and Neptune have a different average composition than Jupiter and Saturn. Instead of being made mostly of hydrogen and helium, a much larger fraction of these worlds is made of hydrogen compounds and rock and metal. In fact, only about a third of the masses of these worlds is hydrogen and helium, with the rest being made of denser materials. Much of that denser material is a high-pressure mixture of water, ammonia, and methane. Methane is really natural gas, while a water and ammonia mixture is what we use as window cleaner. So you can think of these outer planets as being made of several Earth masses of high-pressure window cleaner scented with natural gas. Ew.
Now that we've looked at all 4 outer planets, you may notice something interesting about them. They all have cores of around the same size, 10 Earth masses. This is very consistent with our model of solar system formation, in which 10 Earth masses is the point where rapid gas accretion begins. So we can think of the Jovian planets as all having a similar core of rock, metal, and ices, with the main difference between them being how much hydrogen and helium is dumped on top, from just a few Earth masses for Uranus up to over 300 Earth masses for Jupiter.